the first test that we did looked at a hypothesis where we test whether proportions in several categories are equal to specified values. This represents an extension of the binomial experiment, which we call the multinomial experiment. Instead of having only success and failure as possibilities, we have k different possible outcomes, like you have with the toss of a die, where you have 6 possible outcomes. Then, every problem will be represented in a one-way frequency table where you have observed frequencies. And if you suppose that the probabilities in each category are the same, such as in the case of a balanced die, then you expect the frequencies in all these cases to be equal, and you compare to what you observe. So if what you observe is close to what you expect under the null hypothesis, and these probabilities may, for example, all be equal, but they need not be equal, but they will, of course, all add up to 1. And then you have to check whether this, what you expect, the given probability times the total, is close to what you observe. Then you know that your null hypothesis is probably right. The general procedure tests whether the proportions are equal to specific values, but we do the test by looking at the frequencies and not the probabilities, as we did in previous chapters. So you test whether all of them are equal to specified probabilities against the alternative that at least one of them does not equal the specified value. And you do it by comparing observed and expected frequencies. But I showed yesterday that we can't just look at the square differences of observed and expected, but we have to look at that relative to what is expected. So there's your test statistic, and this is test statistics that we'll be using throughout this chapter, just in different variations depending on the type of table that we're working with and the assumptions that are required. Then your rejection region is always this test statistic value, or rather this test statistic, has a chi-square distribution with k minus 1 degrees of freedom, k being the number of different categories. You will always reject when the chi-square test statistic value is large enough, where the critical value is given by the significance level again, and k minus 1 degrees of freedom. So it's always an upper tail test. Today I continue with the next set of problems, namely when category probabilities are not completely specified, but they are functions of other parameters, and when the underlying probabilities are continuous. So, first of all, in your textbooks, theory and examples are given on page 7 to 8 to 7 to 9. What do I mean when I say chi-square, that's a chi-square goodness or fit test, when the probabilities are functions of other parameters? Remember, it's all about, are probabilities equal to specific values, but now these specific values are determined by probability distribution. So it often happens that probabilities are hypothesized to depend on a smaller number of parameters. Say theta 1 to theta n, that's the parameters, and these parameters are always less than the number of categories. Then a specific hypothesis involving the parameters yields specific probabilities, which are then used in the chi-square test. So you have to calculate your probabilities first, they won't be given. For this purpose, I'm going to consider 4 examples. The first one is where we're going to look at the frequencies and determine whether these frequencies are similar to, can we deduce that these frequencies come from a Poisson distribution with a given lambda. In other words, in this case, we know that the Poisson distribution has only one parameter, namely lambda, and now all our probabilities in the problem, all the frequencies, are functions of the Poisson distribution. And that has one parameter, that's the theta 1 that I'm talking about, and that's lambda. This example is not in your textbook. It's only in the slides. The next example that we're going to consider is example 13.2, but where I've simplified the problem formulation. There we're going to look, as always with a binomial, at the number of successes and see whether the frequencies can be associated with a binomial experiment with a given n sample size and probability of success p. So those two parameters, theta 1 and theta 2, in the first one represents the sample size and the second one the probability of success. The third and fourth example are examples where we work with continuous data measurements, on the one hand from a uniform distribution and on the other from a normal distribution. For the uniform distribution, we know that we have two parameters, the lower limit and the upper limit, and that's our theta 1 and theta 2 now. And that is example 13.3. And 13.4 look at normally distributed variable with a known mu and known sigma squared. So that's your two parameters there. So these different probability distributions will determine the probabilities. So we have to calculate the probabilities given the known distribution with known parameter values. And then we can compare what we expect if that was true to what we observe. What all these have in common is that they're all tests of goodness of fit to specific distributions with known parameters. Very important. This is the theorem and the general hypothesis testing procedure that we looked at yesterday, and that's going to remain our basic procedure. In this section, the only difference is that the probabilities are not explicitly given, but needs to be calculated using the appropriate probability distribution. But the same basic test procedure will be used as for those illustrated in the first lecture. So, recall that for the discrete case, we have probability mass functions, and for the continuous case, we have probability density functions, each with its own formula for probability mass or density function. So, what you need to remember in the discrete case is x is defined from 0 to infinity. For the binomial, it's defined number of successes from 0 to n. And for the uniform, there's your density function, and it's defined between lower limit a and upper limit b, and the normal is dependent on mu and sigma, where x, your normal random variable, is between minus infinity and infinity. Let's consider the first example. It is generally thought that misprints in newspapers occur at random. Now they occur independently of each other, but it's believed that the number of misprints per page can be expected to obey a Poisson distribution with parameter 1.2. So on average we get 1.2 misprints per page. Now we want to test this belief, and for that 200 pages were selected randomly from newspapers and examined, and the misprints on each page were noted. And the data are given as follows. A one-way frequency table, which can be arranged as columns or as rows. What does this tell us? There was 200 pages examined. In 43 cases, there were no misprints on the 43 pages, there were no misprints. On 69 pages, there were 1 misprint. On 53 pages, there were 2, and so on. 5 or more, you can see that there were only 6 pages on which there were 5 or more misprints. So, usually we can continue up to infinity, but we stop at the frequency where it gets smaller. Now, we are working with categorical data, categories 1, 2, whatever, and in this case, although the number of misprints are 0, 1, 2, 3, 4, 5 or more, the meaning of each category, we can number the categories 1 to 6. What is given is this always, and then you have to check, is your total 200 as indicated, and this will be given. Now you have to determine whether these frequencies can be assumed to be from a Poisson distribution. How can we do that? The number of misprints is your random variable. So we want to test whether the number of misprints has a Poisson distribution. So this is your x, taking on values 0, 1, 2, 3, 4, 5 or more. So you can calculate the probability that x is equal to 0 under the assumption that you have a Poisson distribution with lambda equal to 1.2. And that's what you have in the next column. The probability that x is equal to 0 is e to the minus lambda, lambda to the x over x factorial. But x, in terms of the categories, this is your x, and these are your categories. So you can see that if you work with category 1, it's actually you want the probability that x is equal to I minus 1. So that's where my general formula comes from. But it's the same as probability that x is equal to x, e to the minus lambda, lambda to the x over x factorial, e to the minus lambda, lambda to the x over x factorial. It's the same thing. So there's your probability. This is probability that x is equal to 1. And this is probability that x is equal to 2. If we use notation from chapter 3, probability that x is equal to 3, probability that x is equal to 4. And the last one is important. 5 or more. X greater or equal to 5, but you don't have those values, but you have that all of them add up to 1. So 1 minus the probability that x is less or equal to 4 is 0.0078. Note that they need to add up to 1. So you always check that your frequencies add up to the given total, that your proportions add up to a value of 1. Next step then is to get your expected frequencies. You have your observed frequencies, these are your NIs, and now you have to get your expected frequencies. And those are N200 times the probability in each category. Category 1, category 2, and so on. So here you have 60.24 is 200 times 0.3012. My numbers that I've given here are rounded. Always work with as many decimal places as your calculator would allow, right until the end. Then you may round. So 72.28 is 200 times 0.3614. And so you do for all the categories 0.0078 times 200 is 1.56, and you check that the total is 200. It must be the same as your original observed frequencies. So these you can also indicate it by your expected frequencies, capital letter NI. Now, your next step is to compare your observed to your expected frequencies. Square those values and divide by the expected frequency. So there you have it. In this case, it is 43 minus 60.24 squared divided by 60.24. And that will give you 4.934. What you have to remember, you have to do that for every category, but There's the but. You are not allowed to have a frequency, expected frequency smaller than 5. So what do? The test is not valid if you have a frequency smaller than 5. So what we do is we need to combine adjacent categories. When the expected frequency in a category is less than 5, adjacent categories must be combined. So what we do is, instead of working with 5 or more, we work with 4 or more. And the frequencies that we had for 4 and 5 or more was 8 and 6. Now we combine them into a new one, 14. So instead of 5 or more, we now have 4 or more. Instead of an 8 and a 6 separately, we have 14 now. Instead of the theoretical probabilities of 0.0260 and 0.0078 associated with 4 and 5 or more, this becomes 4 or more now. Still, your proportions add up to 1. Still, your observed frequencies add up to 200. Likewise now, 0.0338 times 200 will give you 6.76, and 200 is the total of your expected frequencies there. And now these will remain the same, but now you have to calculate your new deviation in this new category. So that's 14 minus 6.76 squared divided by 6.76 according to this formula again, and that gives you 7.754. You see that this is now greater than 5, so we can continue now. But now we have only 5 categories, not 6 anymore. And our test statistic value is the total of all the so-called cell chi-square values. In your first category 1, that's your chi-square value. For your second category, that's your chi-square value, called cell chi-square values. And the sum of all the cell chi-square values is 15.743. Now we are ready to perform the complete test. First of all, the null hypothesis is always the hypothesis with everything known. So if we suppose that it has a Poisson distribution and suppose that lambda is equal to 1.2, we can calculate the probabilities, otherwise we can't. So that's why that's always your null hypothesis, against the alternative that it's not. And then you have to get your rejection region. You will always reject when your chi-square test statistic value is large enough. But before you can determine the critical value, you always have to calculate your test statistic value first. Because in calculating your test statistic value, your number of categories are determined. You have to combine adjacent categories if required, such as in this case we had to combine, and we ended up with 5 categories, not 6 like we started off with. So our critical value is determined by the final, what happens in the calculation of your final test statistic value. Therefore, we always complete the table first before we do the steps of the actual hypothesis test. So the critical value is 9.488 because we have only 5 categories, but 15.743 is larger than that critical value, so the null hypothesis is rejected. This is also confirmed by looking at the p-value. The p-value can be obtained exactly or more exactly than in the case of table 8.6 by using table 8.10, where for certain degrees of freedom you are given p-values. So you, in the column for 4 degrees of freedom, you look for 15.743 and you will see that that's associated with a p-value less than 0.005. I suggest you take out table 8.10 and make sure that you followed what I've just explained. So you end off by concluding that the sample evidence suggests that the data do not have a Poisson distribution with lambda equal to 1.2. The next example is example 13.2. I've simplified the formulation of the problem. So, simplified, it means test on a 1% level of significance whether x, the number of yellow round-shaped seeds in a randomly selected pot, has a binomial distribution with n equal to 4 and p equal to 9 over 16. So, given this simplified formulation, it means you have to test whether some variable has a binomial distribution instead of a Poisson that we had previously. We're given the two parameters for the binomial. What this is about is they investigated a large number of pods from a certain tree, but they were interested in specifically inside these pods. There are at most 4 seeds in a pod, and they're interested in seeing how many of these yellow round-shaped YR type seeds were inside the pod. So, 269 pods were investigated. In 16 of them, no YR seeds were found. In 45, one YR seed was found, and in 26 cases, 4 of these yellow round-shaped seeds were found. Again, we number our categories from 1 to 5, but the values of our random variable is 0 to 4 because x is number of successes. Success is a yellow round-shaped seed, and therefore that's our random variable. Once we have that, we now have to determine if this random variable really had a binomial distribution, what would the expected probability frequencies be? But before we can get the frequencies, we need to get the probabilities. So, while that is what you usually would be given, you can check that the total agrees with what the experiment says it should be, and then you can calculate your theoretical probability. Again, this is a probability that x is equal to x0, but which you can express in terms of the category numbers. So I've given it there in terms of the category numbers, but you can also say it's probability x equal to x if that is your x, and that is the normal n combination xp to the x, 1 minus p to the n minus x. So probability that x is equal to 0 using the binomial formula is 0.0366. You do it for all the other categories, x equal to 1, 2, 3, and 4, and you get these probabilities, and you have to check. Do they add up to 1? Then you can get your expected frequencies. It is the total of your frequencies, so 269, times the given probability. So 0.0366 times 269 will give you 9.86. And similarly for the rest, and check 269 must be the total. Your expected and your observed must be the same. Now you can see your expected frequencies are all greater than 5. So you don't need to worry about frequencies being too small. You don't need to combine adjacent categories. You can calculate the chi-square values everywhere. So this, for example, let's just look at that again, is 16 minus 9.86 squared divided by 9.86 will give you 3.823. Likewise, the following categories. And then your test statistic value is obtained by adding all your cell chi-square values. So 3.823 plus 0.636 plus this will give you 4.582. That's your test statistic value. Now you're ready to do the complete hypothesis test. However, Please be careful not to confuse the parameter of the binomial distribution with the number of trials, the total number of frequencies. You are repeating a binomial experiment 269 times. For every one of the pods that you pick, there's a probability of 9/16 of getting a yellow round-shaped seed, and there's a maximum of 4 seeds or there are 4 seeds in a pod. So you always know that your n is equal to 4 for each pod, but you have 269 pods. So the test are the frequencies from a binomial distribution with known parameter values. There's your null hypothesis. It has a binomial distribution with given parameter values. The alternative is that it does not have that. You get your rejection region when chi-square test statistic is large enough. Under the null hypothesis, assuming binomial distributed frequencies, you get 4.582 is the test statistic value from the table, the completed table. So I suggest you always complete this table, then do your test. All the expected frequencies are greater than 5. For critical value, there are 4 categories. So your degrees of freedom is number of categories minus 1. Sorry, there are 5 categories, so your number of degrees of freedom is 5 minus 1, which is 4. Critical value is that. So your rejection region is if it's larger than 13.277, or if your p-value is larger than the given significance level. There's a mistake here. The alpha was 0.01. So this must be 0.01. You will reject. Now I recall what the story was here. I looked at table 8.10 without looking at the critical values, just using table 8.10. You will note that the p-value is greater than 0.10, so it's not smaller than 0.01, which means the null hypothesis is not rejected, as you can see by comparing your test statistic value with your critical value as well. And therefore, since the chi-square is not larger than the critical value, and since the p-value is not smaller than your significance level, your null hypothesis is not rejected at a 1% level of significance, and you can conclude that sample evidence suggests that the data have a binomial distribution with n equal to 4 and p equal to 9/16. In the next example, we move to continuous distributions. We're going to look at the chi-square goodness of fit test when the underlying distribution is continuous. Theory and examples, page 729 to 730. For continuous data, we need to categorize the data first. In other words, summarize it in a frequency table in order to perform a chi-square goodness of fit test. So example 13.3 asks the question, does the sample come from a uniform distribution with known parameter values? This is about the time of onset of labor amongst expectant mothers. And they say that the time of onset of labor is uniformly distributed through the 24-hour day. So to see whether it's uniformly distributed, we can divide the day into time periods of equal size. 24 divided by k, and then if it's uniform distributed on the 24-hour day, it means that the probability of observing onset of labor in any given category will be 1/k. So in this case, we divided it into 24-hour periods, which means A is equal to 0 and B is 24. and then your density function is 1 over b minus a, so it's just 1 over 24. We know in the case of the uniform distribution that the probability that x lies between two limits is the cumulative distribution function in the upper limit minus the cumulative distribution in the lower limit, and it's given by this expression. And in this case, because we're considering 1 hour periods in a 24-hour day, it's just x over 24 or 1 over 24, since we're looking at a time period of 1 hour. So if it's uniformly distributed over 24 hours, and we consider intervals of 24, you can see that it will be 0.042, the probability of onset of labor within any given hour. So let's look at the data that's been given from example 13.3. The first two is what's basically given in your notes, the time interval and the number of onset times. Note we have 24 categories. The time intervals associated with each category is given next to that. The number of frequencies, in other words, 52 mothers. Onset of labor for 52 of these expectant mothers were between 12 and 1 in the middle of the night. And 59 had onset of labor between 11 o'clock and 12 o'clock. So, and all in between, we assume that that's uniformly distributed. Note that there were a total of 1186 mothers being observed. Note that the probabilities add up to 1. Note that because we have equal lengths of time, the expected frequency under the uniform case, all of them is 0.042 times 1186. 1186 times 0.042 gives you the expected frequency, and they're all the same. They all add up to 1186 again. And now you can get your cell chi-square values. You compare number actually observed between midnight and 1 o'clock is 52 compared to expected 49.417. Get that difference, square that difference, and divide by 49.417. That gives you the cell chi-square for the first category is 0.135. And you do it for all of them. All your expected frequencies are greater than 5, so you don't need to combine anything. Remember, you look at expected frequencies in order to decide whether to combine or not. Then you add all these cell chi-square values, 162.77, and then you can do your test. So your null hypothesis is that it has a uniform distribution over 24 hours, or against the alternative that it's not. You are given an alpha of 0.01. You will reject when the chi-square is large enough. The chi-square value obtained is 162.77. All the expected frequencies are greater than 5. Therefore, you can get your rejection region right away. You have 24 categories, so your degrees of freedom is 23. Your critical value then is 41.637, which means your observed statistic value is greater than your critical value, and the null hypothesis is rejected on a 1% level of significance, and therefore you conclude that the sample evidence suggests that the sample is not from a uniform distribution with these parameter values. The last example. Does the sample come from a normal distribution with known parameter values? Now, this particular example is a bit complicated. We will give you the frequency distribution, but let me show you how they obtained the info that they give in the notes. They say the developers of a new standardized exam wanted to satisfy the following criteria. The actual time taken to complete the test is normally distributed. The mean must be 100. And exactly 90% of all students must finish within a 2-hour period, within 120 minutes. In the pilot testing of the standardized test, 120 students are given a test and their completion times are recorded. And for a chi-square test of goodness of fit to a normally distributed completion time, to test whether it's normally distributed, it's decided that 8 intervals should be used. So you have to divide the total time taken into 8 intervals. The criteria imply that the 90th percentile of the completion time distribution is 120 minutes. That's 2 hours. They've given that. But remember the 90th percentile of Z, of the Z distribution, standard normal. 1.28 is P 0.90 is 1.28 for Z, for the standardized normal distribution. In other words, what I'm saying is probability that Z is 1.28 is 0.9. But we know the relation between Z and X is Z is X minus mu over sigma, which means X is mu plus Z sigma. So that's what we have here. That's your mu plus the Z from here, Z sigma. But sigma is not given, but we're given that that X must be less than 120, less than 2 hours. So this relation, 100 plus 1.28 sigma must be equal to 120, yields that sigma is 15.63. If you simplify, if you set this underlined here in red equal to 120, you get that sigma must be 15.63. Also remember that for the normal distribution, the probability that X is between A and B is not 5B minus 5A, it's phi of the standardized B and the standardized A. Standardized B and standardized A you get from the standard normal distribution. So, if we were to divide the range into 8 equal intervals, it means 100 divided by, or 100 divided by 8. And that will give you 12.5. So if we work with probabilities, it's 1 divided by 8, and that is 0.125. Remember, I'm dividing my total probability into 8 equal intervals. So that means we need to get the following percentiles: 0.125 or 12.5%, then 0.25, then 0.375, 0.375, and then 0.5, and so on. So let me just rewrite that. So you get probability to the left of 0.125, then 0.25, then 0.375, then 0.5. And what's the probability? What's the value of Z with a probability 0.5 to its left? It's the median of Z, and that is 0. And then to the right, 0.125 to the right of 0.5. You just add the 0.125 to the right and continue like that. But what is this Z then that is associated with this probability? It's minus 1.15. The Z associated with this is probability Z less than Z. These are the probabilities and these are the Z's. This is minus 0.67. This is minus 0.32. This is the Z is 0. Then this is 0.32. This is 0.67. And so on. So that is then why we get to the following Z intervals. That's also given in your textbooks. The 8 intervals to the right hand side is 0, 0.32, 0.675 and so on. And then you have to translate again to x's. So you have your Z intervals and then you're going to get your x intervals. But it all comes from those probabilities that you've added, that you've divided the 0.125 intervals. So that gives the following. The probability that Z is less than minus 1.15 is that 12.5%, 0.125. But now you have to get from Z to X, so that is X is mu plus sigma Z. Mu Z is negative, but there's your sigma, so it's a probability that X is smaller than 82.03. So you have to get to actual marks, not to, you can't stick with a Z interval. So that's what you get here. These are your 8 equal sized probability intervals, minus 1.15, minus 0.675, and so on. But it's symmetric, so you can see minus 0.32 to 0, 0 to 0.32, minus 0.675 to minus 0.32, 0.32 to 0.675. So these are all symmetric around 0. So this is symmetric around 100. This is in terms of X and this is in terms of Z. So your completion times for this test is then we expect these to have equal probabilities. And now what we observe is 21 finished within 82 minutes. 17 between 82 and 89.45 minutes and so on. And 10 took more than 117.97, which satisfies the requirement that that 90% should complete within 120 minutes or 2 hours. But there was also 120 students in total used for this experiment, so you can check that it adds up to 120. The theoretical probability for each one of these categories is 0.125, and that's because we chose to divide into intervals of equal probability. This can be totally different. You can choose your regions differently. The theoretical probabilities need not be the same. This is only for this particular example. But given then these theoretical probabilities that add up to 1, you can get the expected frequencies, which is 0.125 times 120 will give you 15 in this category, for example, for your expected frequencies. And it's the same for all of them. They all add up to 120. Those agree. Your probabilities is equal to 1. You've done all the checks except all these 15s are also greater than 5. You've checked that. And now you can calculate your cell chi-square values. So 2.4 is 21 minus 15 squared divided by 15 is 2.4. And this is 17 minus 15 squared divided by 15 and so on. And that gives you, in the end, a value of 7.73, which is your test statistic value. We will give you these intervals, or at least these ones. And then you can continue. So you don't need to worry about how to obtain these intervals like you had to do in this example. We'll give this to you and tell you to test whether this has a normal distribution. And also remember that these intervals need not be chosen such that the probabilities are equal. But for any interval, you can calculate the probability that x is between certain limits if you know that it has a normal distribution. And you can compare that to your observed frequencies. So there's your test. You assume that it comes from a normal distribution with expected value 100, variance 15.63 squared, against the alternative that it does not. You're given a significance level. You reject when your test statistic value is large enough. You obtained a value of 7.73 from your table. You check that all the frequencies are greater than 5. Therefore, you have 8 intervals, which means degrees of freedom is 8 minus 1, namely 7. That's 12.017. Your test statistic value is not larger than that. Therefore, you will not reject the null hypothesis, and you can assume that the sample is from a normal distribution. Now you know how to test whether a set of data is normally distributed. You can divide them into categories and see whether it can be associated with the normal distribution. A similar example is which is also your homework, is exercise 4. Thank you, ladies and gentlemen.